Hello, I'm Daira Hopwood. Today is the day of anti-fascist struggle in Croatia. I'm here for that. The reason I mention that is that that's one of the reasons I got into Zcash, and I think that you can't have privacy without financial privacy. And that's what we're trying to do, and that's what we're trying to maximize for the most number of users. So how to do that? These are the slides are here. So this is basically my opinion on how to do scaling. And the design space is huge. So I've only got a 20-minute talk, so I'm only going to focus on the things that I think I've been working on. Okay, so horizontal scalability is, like Nathan said, you can add more resources to the network and increase its capacity. But there may still be bottlenecks, and there may still be design changes that we need to make after we've introduced the scalability protocol in order to address those bottlenecks. So we're not demanding perfection from the protocol, but we want it to be able to scale to a very large number of users without compromising privacy in any way. So it doesn't have to be a direct continuation of the Zcash blockchain. What we're likely to do is create a test network that will be running a different protocol, and because that gives us a lot more design freedom in how we design that protocol without worrying too much about backward compatibility, and then somehow transfer the ZEC token and people's existing holdings in ZEC onto that new network. Okay. So what exactly do we want to do besides the main goal of scalability with privacy? We need to support light clients who don't have to trust some other full node that's connected to the network. So the light clients should be able to verify consensus on their own with a reasonable amount of bandwidth for and storage for a light client. So something that you would run on your phone in practice. Nathan was talking about it having been possible to run Bitcoin full nodes on a mobile phone. That's completely impractical now, and it would be for Zcash as well. So we want to also reduce the cryptographic assumptions. So many people are worried about the trusted setup, the fact that there's a trusted setup at all, even despite the improvements we made to the MPC protocol in Sapling. So it would be nice to have if we could reduce those trust requirements and maybe not require quite as exotic assumptions involving pairings. Transaction malleability is important because you want the payer and the payee of a transaction to have a reliable indication that the transaction succeeded. And transaction malleability interferes with that. Okay. We're not trying to reinvent Ethereum. For the time being, we don't need general computation on the blockchain because that would be hard. It's hard enough to support privacy and scaling together than general computation. We don't need to support transparent transactions at all. So what convinced me of this actually was Sarah Michael-John and her group's paper that came out around Zcon last year, sort of studying the interaction between transparent and partially transparent and shielded transactions. And that basically has convinced me we need a fully shielded protocol. And it's actually too hard to support Bitcoin script in R1CS circuits, which is what I'm going to suggest using for scaling anyway, so we couldn't support transparent. This is basically justifying why we're not trying to reinvent Ethereum. Reducing latency there there's probably a latency privacy trade-off, which is unavoidable to some extent. So there are changes we can make to the consensus protocol to improve latency, and then there are others that might increase latency. It's not entirely clear how it'll turn out. And all these things which are not going to be in this talk. Okay, so certain privacy properties are quite easy to achieve. If you just want to hide amounts without hiding the transaction graph, you can do something like confidential transactions. So basically how that works is you have commitments to the values that you're sending, and because the commitments are homomorphic, you can add up the commitments and keep the amounts private. So that pretty much works as a way of hiding amounts, but it doesn't work for hiding anything else. So what we want to do is have the same strong privacy guarantees that Zerocash had and Zcash has now, for the fully shielded subset. And yeah, if you watch Ian Meyer's talk, Satoshi has no clothes, it goes into this in much more detail and describes the attacks that are possible because the transaction graph isn't fully hidden. Okay, so this is basically my proposal, and it has 4 components. So it turns out that it isn't really possible to do it any more simply than this. You need all these 4 things. So sharding allows you to that's what gives you the horizontal scalability for arbitrary transaction, well, almost arbitrary, to support like clients. You can do recursive validation. So what that means is that you're using SNARKs to validate other SNARK proofs. Sharks. So this is a new kind of proof system that allows us to reduce trust assumptions. So basically, you have a low-level proving system, which is kind of like bulletproofs. It doesn't rely on a trusted setup. And then you have another proof system on top of that, which provides the performance for validation that you need. Because bulletproofs on their own have linear validation time, roughly. So you can, by taking a hybrid of those, you can get both the reduced setup assumptions and the performance. And so currently Zcash broadcasts all transactions to all potential recipients and all miners. That doesn't scale. So we need something to replace that anonymity mechanism. Because currently Zcash, it effectively has an anonymity network built in, which works by broadcasting everything, and then you try and decrypt all the transactions with your key or keys, and then you know which ones were directed to you. But that doesn't scale, so we need to find another alternative, and mixed nets are the best studied alternative. Okay. This is kind of a diagram of the proposal for sharding. So time going down according to the arrow, and we split the blockchain into shards, so 3 of them in this diagram. And then we use the SNARKs to kind of summarize each block, each sharded block in each time unit. So these transparent triangles here, the apex of the triangle represents a summary of that shard in that time period. And then you have miners summarizing the summaries, and that gives you a small amount of information for each time period that you need to validate. And then you can have, that by itself will provide a very good scaling improvement on its own. But then you can do the same thing that the Coda protocol does, for example, and you can summarize the time period summaries, and then you have a succinct representation of the current head of the chain. And if you validate that, and it indirectly validates all of the other information, so the whole historical blockchain. Okay, so let's go back and sort of explain the blockchain model. I assume you basically know how blockchains work, but the thing that's important to note here is that the consensus rules, some of them are associated with blocks, and some of them are associated with transactions. And the ones that are associated with transactions, in Zcash at least, are independent of all of the other transactions in the block. They have an anchor, which is the summary of the shielded note state at some previous block, but they can't depend on other payments in the same block. So unlike Bitcoin, for example, where you can create two transactions together and the input of one refers to the output of the other and then mine those in the same block, you can't do that in Zcash because the Zerocash protocol doesn't allow it. So let's embrace that and sort of use that limitation, or rely on that limitation for scaling. There's one exception to that, which is you have to prevent concurrent double spend. So double spending transactions that would be in the same block or the time period. Okay. This talk is only about the payment layer. So if you consider layer 0 is the consensus protocol and the proof of work, the mechanism to allow nodes to agree that something has happened. Then layer 1 is the payment protocol, which implements the shielded functionality. And then layer 2 would be things like Bolt and Lightning. And this talk is only about layer 1. So there are things that we would need to do at layer 0, the consensus protocol as well, because current consensus protocols don't run at anything like the sort of the physical limits on communication and bandwidth. So if you want to use those resources efficiently, you would need to do things at layer 0 as well. This talk is about layer 1. So let's explain basically how Zerocash or Zcash works. We use, I'm going to assume that you know how the UTXO model in Bitcoin works. So you have transactions which have outputs, other transactions have inputs that can refer to those previous outputs. So in Zcash, the things that carry value are called notes, and they have a value and an associated address. And then, so when you spend a note, you're proving that the note exists in a commitment tree. So it's the output of a previous transaction. And that uses something called a note commitment. And you also have a nullifier, which is linked to the commitment. So the circuit can link it to the commitment, but if you don't have any other information, so if you don't have the private keys associated with the address, you can't link those two. So when you spend a note, you reveal the nullifier, and that's what prevents double spending. So if two transactions were to reveal the same nullifier, or actually the same nullifier in a single transaction as well, then that would be a double spend. Okay, have I covered everything there? Yeah. So this state of the commitment tree and the nullifier set is called a tree state. And the notes that are unspent are the ones that have a a commitment in the commitment tree, and no revealed nullifier yet. Okay, zero-knowledge proving systems. So the important thing here is that when we statements are things that we're proving. They have instance variables which are public, and they're publicly revealed in the current protocol. And witness variables are the things that we don't want to reveal, like note values or private keys. And how we're using the zero-knowledge proof system is that we can find a short proof of something, and we don't reveal the witness variables or anything other than the fact that the statement is true for the instance variables and that someone knew the witness. Okay. Yeah, so important point there. We're not just proving that there exists a private key that satisfies the statement. We're proving that whoever created the proof knows it. And that's important when we're talking about private keys, because we know that the private key exists. We just need to prove that the transaction creator knew it. Okay, and you can verify these things non-interactively. Some more details. So I mentioned this before. In order to know that you've received a transaction, all of the transactions are broadcast, and the output's encrypted. So you have the private key that will do the decryption. And so that can be either because you're the receiver of a transaction or because you have a viewing key that authorizes you to see the content. And then, yeah, so you decrypt it, and that's how you know that the output note is yours. Notice that this doesn't depend on soundness of the proof system. It only depends on privacy of the encryption. There's one exception to that to do with unlinkability of diversified addresses, but don't worry about it. So for Sapling, I don't think I need to go into detail on this slide. Okay. Something that is important about Sapling is that you can separate the authorization for spending a note from making the proof. So doing the authorization only requires a signature. It's like a Schnorr signature. And so you can do that on a hardware wallet. And then actually doing the proof. So the skill using the Japanese abacus here is anonymous. And he's creating the proof. And then the proof goes, the transaction gets broadcast, and it eventually gets into the chain via miners. So what are the bottlenecks here? Well, all of the full node validators have to validate every transaction. They have to update the commitment tree. So in order to be able to correctly validate future transactions, they need to maintain the commitment tree and sort of update it. It's just a Merkle tree. They have to update the nullifier set, and that's currently just a flat set, and it's not represented as a tree. You have to broadcast all of the transactions to the validators and to the potential token receivers. The token receivers have to check each output, which is actually quite expensive, because you have to do a Diffie-Hellman key agreement for each check. The miners have to validate the transactions they're including in blocks. Well, they don't always do that, but never mind. The blocks have to be broadcast. So all of the transactions that were included in the block will have to have been broadcast at some point. And if you're a validator and you're not up to date, so your node has been offline for a while, and this obviously would be true of validators who are on mobile devices, then you have to catch up to the current head and do all of the validation from the point at which you went offline. So all of those are obstacles to scaling. Yeah. So what if a naive strawman solution would be to have the miners validate the transactions and then include zero knowledge, well, it doesn't have to be zero knowledge, but some proof that all the transactions are valid, and then other validators would only need to check that proof. So the problems with that are there's a variable number of transactions in the block, so you can't do it with a single proof because the size of a statement that you're proving in current proof systems is fixed. So you could have a tree of proofs, but that's not the strawman that we're talking about. Doesn't address the bandwidth issues at all. I mean, I guess it does slightly decrease the size of the block, but in the strawman, you're still including all the transactions. You're just also including the proofs that they're valid. So that's not enough. Doesn't do anything about the dissection of transactions or the storage of the commitment trees and the nullifier sets. So they still grow with that bound. Actually, that storage is not that much of a problem. But okay, you said that. Okay, so sharding. That's basically the idea of splitting up a distributed system into lots of pieces. The pieces each operate like a small copy of the system, and then somehow you integrate all of the results from those pieces to get a coherent whole. So at the payment system layer, which is what we're talking about, layer 1, this can be either obtrusive to users or to other parts of the protocol, so wallet implementations, ecosystem developers, or it can be completely transparent. Getting it completely transparent is very technically difficult. We want to avoid the cognitive load on users of having to think about sharding. It's kind of okay if wallet implementers have to think about it. So clarification. So when I sort of tried out this talk on people, everyone I tried it out on misunderstood sharding. So they don't have to be complete copies of the system. You can shard particular subsets of the system. You can. So what we're talking about here is sharding the processing of transactions mainly, and the storage and the processing of nullifiers and the commitment tree. So the design I'm going to be talking about, it doesn't split the anonymity set between shards. You still have a global anonymity set. And it doesn't shard addresses. So addresses are not associated with shards. Okay. Yeah, so we're not promising sort of unlimited scaling because there's going to be some overhead for communication between the shards. And in the Ethereum community, what we're talking about is called quadratic sharding. So basically, you can shard to the on the order of the square of the number of transactions you could support before, because the inter-shard communication is also a limitation. Okay, so I'm going to skip this because I explicitly said that this is out of scope. This is basically layer 0 stuff. how you agree on, for example, a set of transactions to go into a shard in a censorship-resistant way. So each shard still has to be censorship-resistant because what we're going to do is notes will be associated with shards. So if you have a note in a particular shard and that shard isn't censorship-resistant, then you can't spend your note, and that would be bad. This is just one particular design. There may be other designs that don't associate notes with shards, and that has some advantages, but it makes the coordination a lot more difficult. Okay. So some other aspects of proving systems that are incredibly useful for scaling. First of all, the proofs are very short. So proof in Grot 16 is 192 bytes, I believe. So they're constant size proofs. They can be verified in constant time. How much time? It's up. OK. Oh, dear. All right. So recursive, yeah. Come to the scaling workshop, and I will explain the rest of the talk.
Yeah. So just keep talking.
Yeah. So the basic idea of recursive SNARKS is that you use a tree of proofs, and proofs at each layer verify the proofs layer down. So you can verify an arbitrary amount of stuff at the bottom layer, but it's hard to adapt that to Zerocash because of the way that the nullifier set is used. So we need to find representations that are suitable for use in zero-knowledge proofs of the commitment tree and the nullifier set. And the rest of my talk was basically about that.